Right, so the fundamental theorem of calculus. The fundamental theorem of calculus states this is the fundamental. I'll just say what it is. So if a function is continuous, right, it basically says the inverse of an integral. So if I take a derivative, if I integrate something, and then take its derivative, I should get my function back. AKA, these are kind of inverses of each other. Right? And then here, if I take the integral, it's so I get the antiderivative. So basically, it's saying if I take the integral of a derivative, I get back the original thing. And so it's just, or if I take a derivative, if I take an integral of a derivative, I get back the original thing. Or if I take the derivative of an integral, I get back the original thing. With some caveats, right? With a little bit of caveats of how this runs down. Okay. So that's what the fundamental theorem of calculus is one kind of like an inverse of each other. Okay. So let's kind of deal with this the way it is. So here we're going to use the following function. We're going to find the values of, oops, I forgot. I think I left off something. Yep. This is g of x equal to f of x, okay? Or f of the integral from 0 to x f of t. So here we have our f of t. And we want to find the values of g of 0, g of 1, g of 2, g of 3, g of 4, g of 5. And so basically it's like basically what I'm doing here is I want to find out what's the area underneath here. So that'd be g of 1, and then the area underneath all of this, that'd be g of 2, and then here would be g of 3, g of 4, g of 5, and so forth, right? And g of 0 would be 0. So let's go ahead and do that. So g of 0. G of 0 here um, is 0, right? Because if I integrate from 0 to 0, right? Let me write this in. I integrate from 0, and then here I'm plugging in 0, because that's where it goes, f of t. So from 0 to 0, we know this to be 0. So g of 1, 0 to 1, f of t dt. Right? And so here, this is just, what's the area underneath this curve? Instead of actually solving it, what's the area underneath this curve? It's 1 times 2 divided by half. So it'd be 1 times 2 divided by half. And that, of course, is 1. G of 1, or G of 2. I'm just going to add this area. So what I'm adding here, I'm just adding 2 to it. So it's G of 1 plus this, so that'd be 3. Okay. And so for this, and then here we can kind of just estimate from there on. So G of 3, it's going to be estimated to be about 4.3 because I'm adding in, because if I took this little bit, added it here, so that'd be about 1, and I have some left over, so I'm just going to say 0.3. This is an estimate. It could be like 0.5, right? But this is, if I drew my triangle in here, let me kind of clear this up. So if I drew in the triangle, I'm over that, right? So in fact, that this to this, so it's over 1, and I'll just say that's 0.3, just to give it a number, right? But now I'm getting rid of this, right? Now I'm getting rid of this. So this, but notice here, hold on, let me do this. So let me do G of 4 with you. So G of 4. So now when I'm adding this, you're gonna have to do this on homework, so I'm trying to make it very clear. So this will all be positive, right? But here, let me just choose, I don't know, this pink, I guess. This is all negative, right? This is negative value, right? And this up here would be a positive value. So up here I'm adding this, and up here I'm minusing this. And So these two would cancel each other out. So this goes back to being close to 3. 3. I did not click my blue. And G of 5, when we go back to this, oh, this is a T, sorry. And this is a half. Sorry, I'm not getting too well, chat. And then f of 5, we're gonna minus this back out, and so I said that was about 1.3. So if I minus 1.3 from that, it'd be about 1.7. All right, so now we have this. We can graph our g of t. So make a rough graph of g of not of t, but g of x. We'll have x over here. All right, so we're gonna have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so we're going to start at 0, right? So we're going to start here at 0. And then I'm going to increase. I'm going to go up. So here to 1. Go up to 1. At 2, I'm going to reach 3. So it keeps going up, and goes to 3. Here at 4, I'm going to reach, so this is 4. I'm going to go a little bit above that, and then I'm going to come back down by 4. I'll be back at 3. And then kind of down 1.7. So this is kind of a rough graph of it. It's rough, but it's what it is. Okay. And so here we kind of see how what's going on before we do anything, right? So I kind of want to give you a sense of when we get to the fundamental theorem of calculus, where I'm going from a to x, what's going on here? What's going on here? Okay. And so we'll be looking at this in more detail, but it's good to have a sense of what's going on. All right, so now we're going to do it more numerically. All right, so if g of x is from 0 to x of f of t, where a is, it should be an a, shouldn't it? Add an a, sorry. Where a is equal to 1 and f of t is equal to t squared, find the formula for g of x and then calculate g prime of x. Okay. All right, so let's do this. So here, how are you getting these numbers? Oh, okay, let's go back. Let's go back. Let's be very clear on how I'm getting these numbers. All right, so this g of x is the area underneath the curve between 0 and some x, right? And so from here, I'm going, so here, what's the area underneath the curve between 0 and 1? Well, let's start with the first one, between 0 and 0. So what's the area underneath the curve that has no length? 0, right? So let's do the next one. It would be from 0 to 1. So what's the area underneath this curve? Well, the area underneath this curve is, well, it's 1 times 2. It's just this triangle, right? So that's 1. For g of 2, sorry, I'm still kind of out of it today, guys. For g of 2, here we're going to have 3. So what do we need to add? We need to add, let me do this in kind of a light blue. Give me a light blue for a second. We need to add this square here and this square here. Right? So that's 1 and 2. So I'm adding, so 1, I'm going to add the 2 to it because I'm going, what's the area underneath the curve between here and here and here and here? Well, that's 3. It'd be the 1 from here and the 2 from here. And so let's go back. So here, oops, I wanted the blue. So that's 3. Now I'm going to add this area. Well, here would be another 1, right? If I just added the flat triangle, that'd be another 1. So I'd say that'd be 4, but I have a little bit more than 1, so I just roughly estimated this extra bit over 1 would be about 0.3. Okay. of a box. Right? So like 0.3 of a box would look something like this. And I say that's roughly what's here. Okay. Then the area below the curve here, since the curve is negative, we take minus what the curve is here, right? And so this would cancel out this, right? So this area here cancels out this area here equally, so we get back to 3. And then we're going to say this is still negative since it's still below, and we're going to still say whatever this is the same as this. So I estimate that'll be about 1.3 of the boxes, right? 3 minus that will give me this. Okay. Yeah. This. So right now it's all eyeballing. So right now, 100% it's eyeballing. We'll do with hard numbers now. That's what we're doing now. Okay. And then I just, for to make this graph, I just roughly put in 0, 1, 3, 4.3, 3 again, and then 1.7. Okay. So I just eyeballed it for this one. So it's a rough estimate. You'll do something close to it. All right. So here, we're not going to, so here we're going to start at a equals 1 and f of t, and we're going to try to figure out what g of x is. All right. So here, g of x is equal to 1 to x t squared dt, right? So if I just plug in everything, so I'll put a t squared here and a 1 here, and I'm going to try to figure out what the formula for g of x is. Well, if we anti-differentiate t, we get t cubed over 3. We're going to evaluate it at 1 and x, because that's my bounds. So it'd be x cubed divided by 3 minus 1 cubed divided by 3. And if we simplify that, we just get x cubed minus 1 over 3. So what's g of x? G of x is just x cubed minus 1 over 3. All right, now let's take the derivative of this. So the derivative of g of x is equal to x cubed minus 1 over 3 derivative. All right, so we take the derivative of everything. Like a derivative, I suppose. Okay, so here if we take the derivative, well, actually I think it's easy to take derivative from here. So if I take the derivative, 3 comes out, and so this becomes x squared over 3 over 3 minus 0. So this is just x squared. And notice here that here, if I take the integral, I get something. But if I take its derivative, I get back more or less the same function. Because here, g prime of t, if I use the t instead of an x, this would be t squared. Because remember, the function doesn't care. The same thing if I had g prime of h equals h squared, right? The function doesn't care what variable you're throwing in here. It should give you back the same answer. Okay. All right, so that's kind of the fundamental theorem of calculus. Here, if I take its derivative, if I integrate something, I'll get a function, and if I take that derivative, I'm going to get back the same function from what I integrated. That's the fundamental theorem of calculus. So let's look at it. Actually, let me leave this up for a second so we can finish writing it. All right. So that's the fundamental theorem of calculus. That says here, if I take a function and I integrate it between a and x, right, then if I take that derivative, I get back the same function. So integration and derivatives are kind of like inverses of each other. And here, if I take this, which allows us to do this, this allows us to make this statement where f is the antiderivative. All right, so here we want to find the derivative of this function. So we're going to do all the steps and show you kind of a long way for a second. I guess we don't. I guess I don't need to do all the steps. All right, so for here, let's take the derivative, and we're just going to use. So we're just going to write the fundamental theorem of calculus, or FTC. I'm going to write that as FTC. So if you ever use the fundamental theorem of calculus, you can just write FTC. Almost all mathematicians know what you're doing. But so in this case, if I want to find the derivative of this function, so g prime of x is equal to what? Well, we can just use the theorem. And the theorem just says it's 1 plus x squared. That's it. That's it, we're done, right? And so the fundamental theorem of calculus allows you just to, if you're taking a derivative of something that's already an integral. So let's do this. And so this one's a little bit different. And so here I want to find the derivative of this integral. But now notice here, I do not have an x, I have an x to the fourth. And so that changes things. But you can still use the theorem. And so let me kind of explain, see if I can explain how to do this real quick. I'm going to let u equal to x to the fourth. And this is going to be a little bit of a preview of the next section. Preview of 5.5. So I'm going to let u equal x to the fourth. And so here, I'm going to go from 1 to u of secant t dt. And then I'm going to take its derivative. Well, according to the fundamental theorem of calculus, according to FTC, hold on, let me use, so we're going to use, hold on, it's dd, so this will be d du, and then according to chain rule, this will be dx du. I lied, I have that upside down, don't mind my dyslexia. So this is d du, then this would be du dx. So that's chain rule, right? If I have a derivative when I switch out my u, I take the derivative of the inside and then change what the derivative of the upper is. It's still the same concept. So FTC allows us to figure out what this is. This is secant of u, right? This is secant. Oops. I forgot my little c here. This is secant of u. And then du dx, well, this with respect to, I take the derivative of this with respect to x. So x to the fourth with respect to x is 3x. No, I lied. It's 4x cubed. And then I just plug in what u is. And then here I'll have secant of x to the fourth times 4x. Okay, let me now that it's all here, let me explain it really slowly and carefully. If this is not a single variable, right? If this is not a single variable, in this case it's x to the fourth, right? Or whatever, right? Go ahead and make a replacement. Say u is equal to x to the fourth, or whatever this non-single variable is. And then go ahead and switch out your integration. Go from 1 to u, secant, whatever your function is, dt, du, and then you're going to multiply it because of chain rule times du dx, because this is what you do when you take a derivative, right? If you remember, if I had some function, remember if we had like, x cubed or x, so cosine of x to the fourth, right? We said u equals cosine x. And so I had u to the fourth times, and then it was d u dx. So it was the derivative of what this was. And so it times it by sine of x, remember? Oh, I didn't take the derivative now. And so here, if we took the derivative, this turned into times du dx, and so this turned into 3 cosine to the 4th x, and then derivative of cosine will be minus sine, so minus sine of x. Remember how we did this? We're doing the same thing here now with the integral. So we're going to replace this with a u. This turns into just secant u then, and then we multiply by the derivative of what we did here. Hopefully that makes a little bit more sense. All right, I'll let you guys write that down. Let me do another quick example. I think I have more examples on the next page. Now we go over something. So let me just do another quick example with you guys. So let's pretend we had d dx of 1 to the sine squared x times t cubed dt. So how would I do this? I would say u is equal to sine squared x. And so I take the integral. This, according to the fundamental theorem of calculus, would be u cubed, right? All this would be times du dx. And in this case, we'll just have to take the derivative with respect to x. And what does this become? So sine squared x. Well, here I'd have to do another substitution. So this just becomes let me do that up here. U equals sine squared x, so du equals, so if I took its derivative, u prime. So I make this like, so it'd be 2 sine x. So move that out front and then multiply by what this is, and be just be flat cosine x. Maybe I made this a little bit more complicated than I wanted. So I have sine squared x cubed, plug it in here, times sine squared x cosine x, and then if I simplified it, this would be 6 plus that, so it would be sine 8x cosine x. I don't know if that makes things any clearer, confuses things, but it's just another example. So whatever it is here, you just declare that to be u. You do this, figure out what the derivative of that is, multiply it across, and then simplify. That's how you do all these problems. I don't think I'll say anything this bad, though. I think I may have done overkill in making this problem. Who knows? What was did you weird things? Okay. All right, so let's do the last bit. All right, so here. So here we have f average. And so f average, the average value of that. And so basically it says you integrate everything and then you take b minus a, and that's what the integral. They add this in the section, not positive why they put it here, but they have to put it somewhere. So this is what we call f average, and the mean value theorem says there is a number that exists. There's some c that is equal f of c is there is some value of the function between a and b which achieves that average value. So let me see if I can draw this basically for you. I'm confused on your question, Pat. Let's see if I can give a quick sketch of what this might look like. So let's pretend we have some sort of function here. Goes negative, comes out positive, and then comes back down. And we're looking between, oh, let's just say A occurs at the beginning. Oh, no, let's just say A starts here and B is here. Okay. And so if I averaged up all what's in between here, This would be somewhat positive because this would add up negatively, this would add up positively, right? And so I'd say f, I'd say whatever this value is right here, this would be f of ab, whatever the average is, and then here there is some c, which it chooses f average. 2 in the last exam. I'm confused. Was this number 2 in the last exam? Oh, example. I'm confused what you're asking. U prime? U prime of sine of squared of 2x? Yes, okay. I can fix that. So here, the derivative of sine squared of 2x is 2 sine x cosine x. So this is sine squared 2x is equal to 2 cosine x. Okay, so here when I plug this in, so here I let u equal to sine squared 2x. And so here, here fundamental theorem calculus says this is now, I just make this a u, right? Same like we did here. And so this t cubed just becomes u cubed, and u cubed is sine squared x, so sine squared x times raised to the third power. You multiply these two powers, you'll get 6. Oh, I see what I did wrong here. This, I see your question. This should be a 2 sine cosine, which makes this 2 sine 7. Thank you. I made it up problem and I put in the wrong thing. That makes sense? Yes. Okay. Good catch. Thank you. Okay. So let's just kind of run through the f average real quick. So here, I'm going to do an interval from 1 to 2. In fact, let's make this a little more interesting. Let's go from -1 to 2 of the function, and then we're going to see what's the average value. Okay, so the average value, so f average is equal to 1 over b minus a to b f of x dx. So we're going to just plug in those values. So this is my b, this is my a. So it's going to be 1 over 2 minus a minus 1, so plus 1, from minus 1 to 1 plus x cubed, that's x squared, dx. All right. So this is equal to 1/3 times, this is x plus x cubed over 3 evaluated at -1 and 2. Okay. All right, so let's just crunch through this. So this is 1/3 times 2 plus 2 cubed over 3 minus -1 plus -1 cubed divided by 3. I'm going to crunch some numbers real quick. So this gives me, this is 2, this is 8/3, thirds would be, and then plus 1 plus a third. So this would be 3 plus 9 thirds. So 6. 6 divided by 3 is 2. Or you could just chunk it through a calculator. Or you could just chunk it through a calculator. Is that a 7? Yes, this is, the other one was a 7. I'll go back to that. Let me finish this and I'll go back to that. All right, so find a C for which the interval, oops, negative, so it matches, satisfies this. And so we want to find some C which satisfies so here I have 1 plus C squared is equal to 2. And that should occur within the interval. And so here I have C squared is equal to 1. That means C squared is equal to minus 1 and 1. And so technically either of these work. So here, let me draw this real quick. So C can equal, oops, it's not C squared. C can equal 1 and minus 1. And so here we have two answers which satisfy the mean value theorem. Because here C equals 1 is equal to the mean value, and C equals to negative 1. So let me kind of show you. Let me draw it for you. And so here we have, this is x squared plus 1. So it's just x squared raised by 1. We're going to start here at minus 1. And so that's at 2. And then I'm going to go to 2. Like that. Let me see if I can make this a teeny bit more even. And so here, this, and so here we're adding up all this underneath. And so the mean value theorem, so I'll chop off this piece and put it in here. Mean value theorem says if I take the average value, which is this is the average value between this interval here, because there's as much below as there is above, we'll find some C. In this case, we found it at 1 and minus 1 and 1. And so there's, and so here, oops, sorry. So here we can say this, the integral between negative 1 and 2 of in this case, 1 plus x squared, the x is equal to f of C between 2 minus the 1. And here we can have C, so here we can plug in either minus 1 or 1. Both of these make the statement true. Both of these make the statement true. Okay. That there is some mean value for the integral. Okay. All right. Well, that's it for the notes for the day. To answer someone's question, yes, this is a 7. Because it'd be 6 plus the 1. So that makes it 7. Yes. Okay. Sorry, I'm a little out of it today. That's it. And we'll do the next one. Yeah, it says, so find, did I get the C from the previous? Oh, no, I'm just plugging in. I want f of C equal to, so this is what I wanted. I wanted f of C equals my average value, right? I figured out my average value was 2. So I just plug in, instead of x here, I plugged in C, right? This is f of C. Right here. F of C is equal to C, 1 plus C squared over 2. And 2 is my f average. Does that make sense? Yeah. And so here we draw something. So here's the integral, right? So blue is the integral, but here if I use this pink real quick, Here I have as much of the pink below as I do above for this function. And that's where your average value will exist. Or if I add up all this function, where can I make a nice box? Basically, how can I make a nice box that this blue box right here, this light blue box, how can I make the light blue box have the same area as the dark blue box? That's another way of looking at it. Okay, let's go back to the last page. All right, we're still hung up on the one I made up. This is on. I should have made something up. Let's go through this real quick. So here, if I'm taking the derivative of something funny, and the reason I gave you something funny because I can almost guarantee WebAssign will hand you something funny, right? Yeah, Leah was doing a good job explaining it. Here, I'm going to have sine. I'm going to just say whatever this funniness is here. I'm going to say that's u. And then the fundamental theorem calculus says if I take a derivative of this, it's just going to be u of that, right? So this function is this function. But u is sine squared, so it's sine squared x. And then I'm going to raise it to the third power here, right? So sine squared x raised to the third power. So sine squared to the third power would be the same thing if I had x cubed, or x squared to the third power. That's equal to x times 2 times 3, which is equal to x to the 6. Or in other words, sine to the 6. Then I'm going to multiply by one more sign. So if I multiply by another sign, it'd be like that. So I'd get x to the 7th or sine to the 7th. Okay? And then the cosine comes from here. And then the derivative, but the derivative of, and then you multiply by the derivative of whatever you replace it by. So that'd be, in our case, u equals sine squared. So the derivative here is 2 sine cosine. So that's 2 sine cosine. And then I just move the 2 up front, multiply that into there, and then in there. Okay, we're all good? Yeah. I made a complicated one on purpose, but I didn't mean to make it that complicated. Don't worry, I'm super slow today too. I'm still not super with it. Yeah. Can we see page 1 again? Sure. There it is. All right, guys. So that's it for the day. Well, the next section's the fundamental theorem of calculus is a good section. It's a lot of concept, a lot of everything, right? It's just the next section is the substitution rule, and we'll do a lot of problems with substitution rule just to get you used to it. It's not terribly hard once you understand it, but you have to see it a couple times before it clicks. And it's kind of like seeing it's chain rule in reverse. That's literally what it is. But it takes a second to do it. Okay.